Alright, in chapter 12, we're going to focus on oxygen and sulfur, organic compounds that contain those. Alcohols contain the hydroxy group OH. Notice the word hydroxy. Hydro sounds like hydrogen is the first part, and oxy is like oxygen. So here's your O and H for hydrogen and oxygen. Ordinarily on a carbon chain, your chain would be surrounded by hydrogens. However, with a hydroxy group, with an alcohol, one of these hydrogens are removed, and instead you have an oxygen there, and that's bonded to a hydrogen as well. So the carbon's bonded to the oxygen, and then the oxygen's bonded to the hydrogen. The oxygen's in the middle of the two. That's why there's a dash in front of it, because that's the rest of the carbon chain. A phenyl group is a hydroxy group that's attached to a benzene ring, which, if you remember, benzene is a hexagon with a circle inside because it's alternating double and single bonds, but the double bonds are actually shared by all those carbons. When we're naming alcohols, it's actually it builds very well on the previous information we have. For instance, methane is one carbon. Instead of having methane, if we put an OH there, we take off the E and we add OL. Same with ethane. Two carbons is eth, A and E because they're single bonds. If we put an OH there instead, we remove an E and we put OL instead. So alcohol ends with OL, so do the names. When you're looking at the common name, so this is the IUPAC version. That's very systematic. However, there are some that use the common names. What you do instead is you look at the OH group and what it's bonded to. So here's your alcohol. That's why we have the word alcohol here. Alcohol here is bonded to a methyl group because of one carbon, so it's methyl alcohol. Here's the OH group. This is an ethyl group if we looked at it as a substituent instead. So the common names look at the chain as a substituent rather than the base of it. So let's practice some naming. There are 3 carbons here. That means it's prop is the base of it. They're all single bonds of propane. However, the OH group means that we're going to drop the E and make it propanol. It's on the first carbon here if we count from right to left. So it's 1 propanol. Here's our OH group. 1, 2, 3, 4. That gives us butane, because it's a single bond chain. Drop the E, it becomes butanol. You start counting on the side that's closest to the OH group, so we're going to count from the left this time. 1, 2. On the second carbon is the OH group, so it's 2-butanol. And then finally we have this example down here. It's already counted out for you, so it's 6, which is hex. Hexane if it was all single bonds. However, because of the alcohol, we're going to change that to hexanol. We want to count on the side that's closest to the OH group. So 1, 2. 2-hexanol. We also have this methyl group over here, so we can't throw that away. That's on the 5th carbon, so 5-methyl 2-hexanol. Here's some examples of some very typical alcohols. Rubbing alcohol, very important for biological reasons, for sanitation. Notice 3 carbons, so there's prop. It's an alcohol, so there's OL, and it's on the second carbon. This is the common name for it. ethane, there's two carbons here. because there's two OHs, it's diol, because there's two alcohols, and it's on the first and second carbon. And the last one, here's your 3 carbons, so it's propane. It has 3 OH groups, so it's tri-alcohol, and here's our 3. Glycerol is actually used in soaps and for cleaning because the carbon, this portion of the compound, does really well at mixing with oils, and then the OH groups do really good with rinsing it away with water because it's attracted to the water when you're rinsing. So let's practice some naming. 1, 2, 3, 4 carbons. That gives us butane. It's an OH group, so it's butanol, OL. Remember, start counting from closest to the OH, so that's 1 butanol. Here we have 1, 2, 3, 4, 5. That's pentane, and it becomes pentanol. We have an OH group here and a methyl group here. So 1, 2, 3, because we want to count closest to the OH. So on the second carbon of pentanol, there's an OH group, and then on the third carbon, there's a methyl group. And finally, we have cyclopentane, which becomes cyclopentanol. And I don't actually need a number there because of the fact that it's a cyclo. Here we go. Alright, phenyl, as we said before, is a benzene ring with an OH attached. And it's used for antiseptics and disinfectants. Here's some examples of some phenyl rings. Vanilla, we've actually talked about before. Here's actually an ether group inside of it. This is an aldehyde too. Thymol is in thyme for seasonings. These are all cooking products here. Alright, so when we're looking at this, we want to name phenyl here. That's where that part comes from. That's part of the longest chain, is the phenyl. Now we have to look at the substituents. Chlorine is chloro. We're going to start counting at the OH. 1, 2, 3. And we want to make it the smallest number possible, so we want to go towards the direction of this substituent. So 3 chlorophenyl. 1, 2, 3, 4. 4 bromophenyl. So we're going to start drawing some of these. I'm going to give you a minute to do it on your own first. Okay, so let's see how we did. Pentanol is pentane, so that's 5. 1, 2, 3, 4, 5. And on the third carbon, there's an OH group. 1, 2, 3. All the rest of them are hydrogens. Ethyl alcohol. That was the common way of naming it. So we need an ethyl group, which is 2 carbons. And on one of the carbons, we have an alcohol, which would be OH. It doesn't matter which carbon I would have put that in. If I would have put it on the first one, that would have been fine too. 4-methylphenyl. So we're starting with phenyl now. That's the hexagon with a circle inside. And we have an OH group. Now on the fourth carbon away from it, we have a methyl. So here's 1, 2, 3. here we will have a CH3. And here you go. So let's take a look at thiols now. Thiols contain sulfur. So alcohol is OH. Thiols are SH. Same kind of ordeal here, where we have a carbon chain, which ordinarily would be surrounded by hydrogens. However, if it's a thiol, take away one of those hydrogens and put a sulfur there instead. And that's bonded to a H. They have an extremely strong odor. So much, in fact, that if you have natural gas in your house, they've actually added thiols to natural gas in order to be able to detect gas leaks. Natural gas on its own does not actually have an aroma, so they have to add something to it so that way you can tell. Well, this doesn't react with the natural gas, and it makes it so it's an unpleasant smell so people can detect it right away. Some examples. Methane thiol. Notice how they named this. Here is CH3. If it was CH4, that is methane. But because they replaced one of the hydrogens with an SH group instead, they kept the word methane. They just added thiol to the end of it. Methane thiol. Same thing here. Propane. Here's propane here. They took away one of the H's and put an SH there instead. Well, they kept the name propane, they just put the word thiol at the end. Notice after they get past 2 carbons, they put the number in which the thiol exists. So on the first carbon, there's a thiol. Here, propene, so once again, here is the actual part of it. There's a double bond, so it's E and E. They started counting where the sulfur is. So this is the first carbon rather than the other way around. So 2-propene, saying that on the second carbon, there's a double bond of a 3-carbon chain. And on the first carbon, there's a SH. On ethers, notice the line on either side. That's because that's where the carbon atoms are. With an alcohol, on one side of the oxygen was a carbon, on the other side was a hydrogen. With ethers, both sides have carbon. So here's your difference right there. So they're surrounded by carbons on both sides. To name these, you name as if both sides were individual substituents. So for this one, we have a CH3 here. We know that's a methyl group. And a CH3 here. We know that's a methyl group. So it is dimethyl, because there's 2 of them, ether. On this one, we have an ethyl group here, and we have a methyl group here. You do this alphabetically. So it's ethyl, methyl, ether. And then the example down here, we have a methyl group and a propyl group. So methyl, propyl, ether. So this is reviewing everything we've done in this one section. We're going to draw these. I'll give you a minute to do it on your own. Okay, let's take a look at this. We have pent, that means 5 carbons. On the third carbon, there's an OH group. All the rest of them are hydrogens. On B, ethane. So that's 2 carbons because it's F. Thiol means that we have an SH group on it. And the last one is diethyl ether. So ether means that there's an oxygen in the middle. Diethyl means that there's an ethyl on both sides. And ethyl means 2. There you go. So ethers as anesthetics. Ether is probably the most common anesthetic up until the 50s or 60s. The problem is, however, it's very volatile and explosive. Now remember, volatile does not mean necessarily explosive. Volatile means that it goes from a liquid to a gas very easily. Now the fact that it was flammable is a reason why it was explosive. So now they're using different ones, such as ones that contain fluorine and chlorine in it, that aren't as flammable. And that is the end of section 1 of chapter 12, alcohols, thiols, ethers. That's it.